Well, exoplanets have become quite popular to talk about, and I'd like to spend this section going over exoplanets. To define exoplanets, we simply mean that any planet that exists outside of our solar system is considered an exoplanet. And an immense amount of energy has been put into trying to find exoplanets because, of course, these may contain life potentially like ours. So in this particular graph, what I'm doing is I'm plotting the radius of the exoplanet compared to or divided by the Earth radius, and I'm plotting that against the orbital period, which is of course the amount of time it takes in Earth days for that planet to go around its particular star. Now, the line here is the Earth, and the Earth of course goes around the Sun 365-day period, and so you can see that the arrow is pointing to the point on that line where you will see 365 days versus 1, which is the radius of the Earth divided by the radius of the Earth. And you can get an idea then that any planets that we find out there that look about the same size as the Earth and have the same orbital velocity will fall around that plot or that point that we're showing as Earth. And as you jump up, you can see where Neptune would fall, and you would see where Jupiter falls. So one of the things that I think you probably should notice on this graph is that the earliest exoplanets that were discovered were what we call brown dwarfs. And brown dwarfs are a little bit, starting about Jupiter's size, a little bit bigger than Jupiter, and they go all the way up to 75 times the mass of Jupiter. And you start to get fusion in the center of these critters around 13 times the size of Jupiter. So they can even have internal heat being generated in them. And of course we don't call them stars yet because there's so little fusion going on. Well, so a lot of the exoplanets, not surprisingly, that were discovered early were really large brown dwarfs falling up towards the high end of this graph. And then we set a satellite up called the Kepler Space Probe, and that was set up specifically to look for exoplanets. And that probe, the main reason for sending up the satellite was to not have interference with the Earth's atmosphere, so that it could look for exoplanets easier than you could through telescopes here on Earth. And it's been quite successful. If you look at the number of exoplanets that we found, it's considerable, and they're starting now to get more and more close to the size of the Earth. And I'll talk about some of the specific ones in just a minute, but I should tell you that this plot was made in April of 2015. It's now 2016. There have been a considerable number of planets that have been found, but at the time I did this there were about 5,340 exoplanets that had been discovered, and about 1,200 of them had good enough data so that we could plot them on this graph. No doubt that has increased since the graph was made. Now I want to point to a couple of interesting areas. You see K22b there. K stands for Kepler, and K22b is the first, or was the first planet to be discovered in the so-called habitable zone, or another term for it is the Goldilocks zone. This is the zone close enough to a star or just right distance from a star where water can exist on the surface. We call it a habitable zone because we think that water is a requisite for life in our galaxy. And so we're particularly interested in planets that might have water on them, that is H2O in the water phase rather than the gaseous or ice phase. And then take a look at GJ 1214b. That is what many consider to be a potential for a water world. The whole planet may be covered in water. We don't know for certain, but there is some evidence out there that it existed in it. I should say that it exists with water completely covering it. It was discovered in 2009. It's 2.68 radius of size compared to the size of the Earth, and 1.6 days, so it's very close to the star that it's going around. Well, let's go on now and take a look at this graph. This graph is the number of exoplanets that have been discovered each year. The Kepler space probe went up in 2009, and so we started getting a lot better data about 2009, but things seem to really increase in 2014, and the data from 2014 is very comparable to the data in 2015. We're getting a lot of exoplanets that we're finding out there. So we should be, as technology gets better and better, we should get better and better at detecting exoplanets. There are only two ways to calculate these planets, or to determine these planets, two major ways. And the two major ways are, the first way is the radial velocity method. Now when an exoplanet is going around a star, it will force that star to wobble or actually go around a point or an axis. And when that star moves away from the Earth, we can get a red shift on it. And when it moves towards the Earth, we can get a blue shift. And by accurately measuring the amount of wavelength change as the exoplanet goes around that star and shifts the velocity, we can tell not only where that exoplanet is, but approximately how large it is, and get an idea of how far away it is from the star. So very cool stuff going on there. The only problem with this method is that from Earth you have to be looking on the disk that contains the exoplanet with the star, which limits us considerably in the number of planets, exoplanets that we can find. I should also mention that so far with the discovery of all these exoplanets, that we think that maybe as many as 50% of all the stars out there have planets associated with them. And that's really remarkable. Well, here's the second one. This is called the transit technique, or transit method, and it's very simple in concept. What you do is you measure the amount of light coming from the star, and then you wait until you think a planet is crossing it. You won't be able to see that planet, but it will drop in the amount of light that the star produces as the planet goes across it. And by determining, it'll be cyclical because the planet is orbiting, and so by getting an idea of how much decrease there is in light, you can get an idea of the size of that planet and where it is. So these two methods give us a pretty good idea. Again, though, the problem with this method is the same as the other method. The plane containing the star and the planet have to be in such a way that the Earth can look onto it, and we can detect the planet going across the face of the star. So that's the transit method. Now, what I'd like to show you is get some idea of how many Earth-like planets we found. We're limited in the number of Earth-like exoplanets that we found. And this diagram further suggests that we've got a ways to go before we start finding Earth-like planets, and particularly Earth-like planets in the habitable zone. So let's just look at this diagram in terms of trying to see what planets out there that might even look terrestrial. This is a planet density in grams per cubic centimeter versus the planet radius. Now the planet radius here is the planet radius divided by the Earth radius. And 1 therefore would be the Earth, and you can see if you go up that E for Earth as a diamond there. And you also have Venus, you have Mars, and you have Mercury. And that's where the terrestrial planets fall. In addition, you have this empirical fit for the radius, and that's the red line. And then you also have a mass density for planets that would be like Earth if you varied their radius. And you can see that as the green line. Well, I guess the thing that strikes you is there's only really 3, 4, maybe 5 planets that fall in the terrestrial zone. Most of them fall out to the right where that black line is. And that black line is an empirical fit for planets greater than a radius of 1.5 on this diagram. So 1.5 seems to be kind of magical there. We tend to get, you know, some terrestrial, I don't know what's happening down there with the very low densities, but I guess the conclusion that one might come to after looking at this kind of a graph is that at least in terms of terrestrial planets, we're not finding many exoplanets that look like they're terrestrial planets on the basis of their densities.